Hello friends, we are going to learn the concepts of machine learning in this series like linear regression, logistic regression, decision tree, naive-based neural network. We won't go to discuss the very complicated formulas in this series. We are going to discuss the fundamental concepts and we'll also do hands-on exercises using Jupyter Notebook, Python, Scikit-Learn and Pandas. If you want to know in detail, you can join my course. I'll give the link in the description box. Today, we are going to learn logistic regression. If you haven't watched my previous video on linear regression, please watch it. Link of that video is given in the description box. This is one of the most fundamental and critical concepts in machine learning. Let's see how it works. In linear regression, we learned the basics of machine learning for prediction of continuous value. When we had seen the example of office space versus price, we had seen that the prediction was on continuous value. You can see that in this table. But there could be scenarios where we want to classify whether an email is spam or not. It's yes or no type of answer. Is the transaction fraudulent? Yes or no. Is the tumor malignant? Yes or no. So here it is not a continuous value prediction. It is yes or no type of classification, and this is called logistic regression. So when it is a problem of classification, we call it logistic regression. Answer of the question is yes or no type. If it is yes, the result is 1. If it is no, the result y equal to 0. So y belongs to either 0 or 1. 0 is negative plus like not spam, not fraudulent, etc. And 1 is positive plus like spam, fraudulent, malignant, etc. Let us delve more into it. Let us take the case of fraudulent transaction classification. Let's say there is an existing data set that recorded features like customer's age, gender, location, transaction amount, transaction location, transaction time, etc. So there could be many more features. And finally, the result, that is whether it is a genuine transaction or a fraudulent transaction. Now, based on this data set, we develop the model. The data set is called a training data set. Each row in this set is one training example that is used to train the model. And each column, except the last one, is a feature. The last column is the result, sometimes we call target. It holds the information about classification like whether it's genuine or fraudulent. Once the model is built, it is ready to predict the type of transaction. It predicts the probability of the transaction to be classified as fraudulent. For example, if a transaction happens for a customer in an unusual location at an odd time of the day of an amount that is significantly large, it immediately raises an alert. The model generates high probability of the transaction being a fraudulent one. Let's see how the model is trained. We take only the training data where the genuine and fraudulent transactions are all marked. See, the G is for genuine transaction, F is for fraudulent transactions. Earlier, we had seen that the result can belong to either 1, that means it's a fraudulent one, or 0, that is genuine one. Now, during the training of the model, for each example, if it is genuine, it is put in the box 0, or if it is fraudulent, if it is put in the box 1. So, how do we put it in a graphical format? Ideal case would have been if condition is met for fraudulent one, it is marked in the 1 level, and if the condition is met for the genuine transaction, it is marked in the 0 level. So in practice, this is represented by a sigmoid curve. So you can see the sigmoid curve over here. We'll explain the curve more in detail in the next line. The sigmoid curve is represented by the formula sigma z equal to 1 divided by 1 plus e to the power minus z. E is the constant, it's called Euler's number, which is 2.718. In the graph, if the positive value of z is higher, okay, the curve is almost near 1. And if z is further and further in the negative direction, it is almost near 0. And at z equal to 0, sigma z is equal to 0.5. In linear regression, we talked about hypothesis. Here in logistic regression, our hypothesis is h of x, which is sigma z. Value of h will be between 0 and 1. So now we can see the equation becomes h of x equal to 1 divided by 1 plus e to the power minus z. So what is z? Z over here is that whole equation of the w0 x0 plus w1 x1 plus w2 x2 plus wn xn. So what is this x0, x1, x2, xn? So these are all features. So here we have two subscripts for x, that is j and I. So xji means the feature value of x for jth feature and for the ith training example. And wj is the weight for jth feature for each training example. So we have identified the expression for logistic regression, the sigmoid curve. How does it help in identifying the decision boundary? So now we see that there is a plot of some green and red marks. This could be a plot of, say, for example, a chest X-ray. Okay, one side, there is a x1. Say, for example, hypothetically, there is a patch size, and x2 maybe the patch depth. It's hypothetical. Okay, so red ones are where there is pneumonia, depending on the value of, say, x1 and x2, and the green ones with no pneumonia. Okay, so y equal to 1 for the red ones and y equal to 0 for the green ones. So that is given. Now we have to find some boundary lines on one side of which we can say that y is equal to 1, and on the other side you can say that y equal to 0. Okay, so now we come to our hypothesis. What is hx equal to sigma z, which is equal to 1 divided by 1 plus e to the power minus z. We have two features over here. So z is equal to w0 plus w1 x1 plus w2 x2. Okay, x1 and x2 are the features, and w1 is the weight of x1 and w2 is the weight of x2. Now say, for example, hypothetically, w0 equal to minus 3, w1 equal to 1 and w2 equal to 1. Okay. Now we will predict y equal to 1. That means there is pneumonia. Okay, if hx is greater than or far greater than 0.5. Okay, so that means when sigma z will be far greater than 0.5. That means when z is more than 0. So now we know that w0 plus w1 x1 plus w2 x2 is greater than equal to 0. That means when z is greater than 0, it is that. This condition needs to be satisfied. And let's put the value of w0, w1 and w2. So that means minus 3 plus x1 plus x2 should be greater than 0. So that means our x1 plus x2 should be greater than 3. So based on this, we draw the boundary line. So when a new point comes, okay, so a new point comes, so based on whether the value is greater than 3 or not, we predict if it is on the other side of the boundary, we predict that there is pneumonia, and if it is on green side of the boundary, we'll predict that there is no pneumonia. So this is how it works. And now we'll go for a small hands-on exercise using Python, Pandas, and Scikit-Learn. Now we're going to write a small code using Jupyter Notebook and Python and Scikit-Learn and Pandas to study the logistic regression. So these are the libraries that we need, like Pandas, NumPy, Matplotlib, and Scikit-Learn logistic regression. We have already imported that. I have already created one CSV which shows a number of hours that a student has studied and whether he or she has passed that. So this is the data frame, and now we're going to plot it. X side is hours, on the Y side, then it's the color equal to marker equal to X. Let's see how does it look. So this is the scatter plot. Okay, so in the bottom this shows that these are the number of hours that the student studied and they could not pass, and in the top these are the number of hours the student studied and they have passed. Now we'll create the model based on this. Model equal to logistic regression, and now we fit model dot fit df. So model is ready now. Now we see it is w1 and w0. w1 equal to model dot. So this is w0. Now we'll try to develop the sigmoid curve from based on this model. So this is the x-axis, y-axis. These are the points. Now we create this plot. X equal to p dot sort all the points. Let us sort all the points in dot. So these are the x points, and based on that we'll create z. Z equal to w0 plus w1 x. Okay, so that is z. Now based on this we'll create our hypothesis, which is equal to h divided by 1 plus e to the power minus z. E means in p dot exp to the power. So that is our h, and now we plot it. Sure. Okay. So this is the sigmoid curve that we have generated out of this model. It's not very smooth. Now we'll see how to make this plot a smoother one. This part, and instead of x, let's take many such points. Let's put it x all, and we'll use one minimum to maximum divided by 100 equal parts. Now z equal to this all, and h is fine, and it's plot x all h. So this boundary is about showing on the right hand side pass and on the left hand side did not pass. I'll just put the vertical line and stick it a thin line. Put the horizontal line. Line style as dash, some legend just to see the boundary line. Okay, at what position the boundary line is drawn. Let's see, how does it look? Okay, so this is a much smoother curve. Okay, and at 0.5 in the horizontal line, 0.5, where it cuts, we can find the boundary as a vertical blue line. So on the right hand side it will be predicted as passed, and on the left hand side it will be predicted as did not pass. Now we'll do some prediction. Okay, now model dot predict. So what do we predict? If somebody has studied for, say for example, 23 hours, so what does happen? So it's 0. 0 means did not pass. If somebody has studied for 28 hours, okay, so our boundary condition is at 27. So if somebody has studied for 28 hours, he has passed. So this is how you can try with different hours and you can do the prediction. So this is our very small and easy logistic regression code using Python, Pandas and Scikit-Learn. You can also do similar exercises wherever you find this kind of data point. So in this session, we learned the fundamental concept of logistic regression, concept of boundary, and did a small exercise in Python. Later, we'll go deep in understanding the cost function calculation and gradient descent. Thank you.